computer scientist at Argonne National Laboratory in Math and Computer Science, and I'm a member of the Computation Institute here in Chicago. And then my group is collaborating with the CMTS project on this area that we call cyberinfrastructure. Okay, for anyone on the remote side again, I'm Mike Wilde. So our team basically works on what we loosely call scientific workflow solutions, and we're applying it to the problems of the kinds of computing that we do inside the CMTS project and just in this whole field in general. For people that may not have, or not use this term all the time, by cyber infrastructure we basically mean computing technology, but it's the sort of umbrella term that the National Science Foundation and other national funding institutions are using to cover this whole spectrum of massive scale hardware, advanced software, collaboration systems. So those are really the three areas that are roughly involved when we talk about cyber infrastructure. So our specific approach to cyber infrastructure in the context of CMTS and the kind of work we do here is really focusing on two things, but the general spectrum is basically how do we improve scientific productivity through better computing tools and approaches, tools, methodologies, things like that. And we're really focusing on this productivity at two different but very closely related layers. The first layer is how do we make it easier for you, the individual scientist, to get your computing done? How do we make it easier to compute with more focus on your science and less focus on all the minutiae and mechanics that you typically get distracted with when you use the kind of large-scale tools that you use in typical molecular dynamics work. And the second level is now, once we improve your personal world, how do we leverage that technology to improve collaboration? In other words, to improve productivity by making it easier to share what you've done and discover what other people have done, and basically take your individual work and elevate it to the context of collaborative science. Okay? So at the personal level, the first problem we focus on is basically how do you express the work you do in executing typically complex scientific application codes. Your basic toolkit of tools like NAMD and LAMPS and GROMACS and the many other various tools you use in your discipline. How do we basically take those tools and create the cyber infrastructure, the software framework around them to make it very easy to execute them on diverse and ever-changing and ever-scaling resources, on shifting network situations, on how do we deal with the problem of organizing massive collections of files and directories, cataloging them, exchanging them with other people, and things like that. Okay. So that'll be the first problem we're going to be talking about. We're going to be talking a lot about how do we basically make it easier for you to move from different, move your basic science logic, what we call your workflow, from one platform to another. And we're going to do that by elevating the level at which we express the way you interact with tools and systems. Okay. We're going to deal a lot with sort of the problems of data transport. In other words, you can use a single supercomputer to get your work done pretty productively, but then when the next supercomputer comes on the scene, how do you move your data around that? If you have computing allocations spread across multiple infrastructures, how do we make it easier for you to think in terms of a logical level of your tool without having to worry about where a given tool is going to run on a given day or a given instant? Okay. We're going to also deal with issues of security. How do we basically traverse the different security domains that you're going to experience as you use those complex machines? How do we handle failures? In other words, how do we make it so that the infrastructure does the retrying of a failing command or the moving of a command from one system to another when a machine is, say, out of space or down or failing for some other reason, or you have transient failures in your workflow where retries will typically get around that. And then lastly, once we wrap all of this technology together to try to elevate the level that you're going to express your science code, that gives us a unique opportunity because the same techniques that we're going to use to conquer those first set of problems is going to make it easier for us to track, easier for you and then your colleagues to track exactly what you did in your computational experiments and to convey that knowledge, store that knowledge in a database, and use that knowledge as the basis for collaboration. Okay, so just to sort of summarize, we're gonna basically talk about how do we write parallel workflows, how do we make it easy to run those parallel workflows across many machines, how do we record what we call the provenance, so this notion of recording the history of what you've done. Across many scientific disciplines, we're starting to use the word provenance, which is really kind of a word that comes from the study of ancient texts and the studying of, say, a fine bottle of wine or a work of art. The word provenance has been used to track the history of those objects. We're applying the provenance now to track the history of the artifacts you create in your scientific computing. Okay, and then we're also going to be talking briefly about new techniques we're going to try to introduce to allow you to annotate your scientific data and your scientific scripts and tools, much the way you would, say, annotate a picture with metadata in Flickr or any of the other multimedia sharing technologies that you use in your lives outside of science. So this notion of tagging objects is a notion that we want to bring into the science process. So you can tag your data sets, tag your codes, and use those tags to remember what you've done, to act as your scientific logbook, to basically use those kind of tagging query mechanisms to discover the work of your colleagues or of the community at large, and then to use those tags to basically make it easier for people to find your work. Okay. So what my group does, and it's a group that's basically split again between Argonne and UChicago, is our principal, the principal embodiment of our computer science research is a programming language that we call Swift. So Swift is a scripting language, and it's specifically a scripting language for the execution of other tools. In other words, it's a very thin language in the sense that it's not a very complicated language, it's not very rich, it's basically intentionally kept very thin and lightweight because its main purpose is to execute both science codes and the typical scripting language glue code that you have to do when you do computational science. In other words, you're often calling scripts in Shell, in Perl, in Python, in whatever scripting language you happen to be using and comfortable with, to kind of manipulate your data, to pre-process it, to post-process it, to prepare runs and things like that. So Swift doesn't basically replace the mechanisms for doing that. It just gives you a higher level way to express the science code. And I'll probably come back to this theme several times. So sometimes we talk about Swift as the way to write the outer loops. In other words, the highest level logic of your science workflow. If you have to run 100 NAMDs, filter them through VMD, take the output of that, select a set of trajectories, go on to some next stage of processing. We call that whole process a workflow, and in a sense, Swift is the way to express that workflow. It's not a way to write the individual nodes of that workflow, the individual components. It's a way to express the processing at large. Okay? And what we get from doing that is a couple things. So the first thing we're trying to achieve is to elevate the level of abstraction. In other words, elevate the level that you think about when you think about interacting with your tools. When you have to run NAMD, we want you just to think about how do you translate your science into NAMD's input language. We don't want you to have to worry about how do you get NAMD to run on the Kraken supercomputer one day and the Stampede supercomputer the next day, and the differences between their unique and arcane batch command language and things like that. So we're basically trying to get all of the junk, the noise, out of your view and automate that and abstract that in Swift and leave you with just the science logic. Okay, that's the ultimate goal. Okay, and the basic approaches are the bottom four on this slide. So we're trying to, so first of all, Swift is a little bit unique from most other scripting language in that it's an inherently parallel scripting language, but it's also implicitly parallel. So if you've done your own parallel programming in other programming models, such as MPI, OpenMP, a variety of parallel methods in MATLAB or in Python and things like that, in most of those languages, you're explicitly specifying the parallelism. You're saying make this loop parallel, or you're saying send a message from this function to that function across an interconnect. That's what we call explicit parallelism. In Swift, parallelism is implicit, and we'll see soon what that means. But basically, it's one thing that we're trying to remove from your mental job. In other words, if you're sitting there writing a workflow and there's opportunities in that workflow to do parallel programming, we want your script to be able to exploit parallel resources to run faster, to get you an answer faster, to broaden the space that you can simulate and things like that. But we don't want to force you to have to deviate from your science logic to think about how to do that. Okay, so that's the goal of implicit parallelism. The second thing is transparency with respect to location. In other words, it's very rare that you have the luxury of just computing in one place. Most of you that have been doing cluster computing to get your work done have, typically, if you haven't yet, you will soon be exposed to having to use many clusters and other clusters. And you're always in a situation where one cluster is busy, you wish you could get something done, you want to move your work to another cluster, but you're stuck because your script has logic that ties you into the place you wrote it, so you have to now deviate from your science thinking to get your computing done. So this notion of providing the second level of transparency with respect to location is the thing that should free you from having scripts that are tied to running in only one place. The third thing is failure recovery. I alluded to that briefly. You have to sort of stop from your science logic to think about how to put loops in to retry things if you want to make your scripts more robust, or you just have to manually rerun them or go into them and patch them and figure out, well, my workflow got to this point, but then it failed here, so I have to comment that out, and I'll run the next part later. What we're trying to do in Swift is automate that for you, so that Swift knows what part of your workflow completed and what didn't. And it'll just resume where it left off, and it'll know how to retry given parts of the program that failed. It's sort of under your control. You can sort of say, if I have a failure, retry 0, 1, 2, 3 times before you give up and declare that function unrunnable. Okay, and then the last thing we're trying to automate is provenance tracking and to some extent the interaction with metadata systems. The notion of being able to tag your work and the notion of having the Swift language itself tag your work with your work's provenance. So for example, again, using my favorite MD tool, NAMD, if you're doing a NAMD run, Swift should record for you that I used a particular version of NAMD, I ran it on a particular machine, I ran it with this parameter set coming in, and things like that. So that when you're done, you've got a log recording of exactly what ran where, how, under what circumstances, how long it took, what resources it used, and things like that. And you can go back from this audit trail and kind of do a lot of things. You can sort of analyze the correctness of your code to some extent. If you're discussing results with colleagues and you sort of say, oh, this looks kind of funny, did you use this version of NAMD or that version of NAMD? You can answer those questions more methodically by having this kind of audit trail. Okay. So here's a little picture of how Swift sort of looks. You basically run Swift on any host. We typically all work in a Linux or Unix-based world, and that's where Swift runs. It also runs on Windows. It certainly runs on Mac OS. But we primarily run it on Linux. But you can run it on any Linux host. So this will typically be a login host in your computing environment, or some kind of interactive computing host. You could run it on your laptop, but you typically want to run it in a place, since many of your workflows are not going to run in seconds, but they're going to run in hours or days, you want to run it in a place that's persistent. So we often run Swift, for example, under the very handy Linux tool called Screen. I'm not sure if everybody uses that or how many people use it, but it's a very handy tool that retains a virtual window context for you. After you log off of a host, your work stays running, you can reconnect to it. So it's an ideal place to run Swift on an interactive host. And then Swift basically talks to external computing resources that are typically clusters, but maybe clouds, or maybe just ad hoc desktop resources, or other kinds of less organized parallel resources. We're actually doing work now that's extending Swift into GPUs and other accelerators. But by and large, it sends work from a single host out to parallel resources. Okay, so what does it look like? So this is an example that we actually still have underway. It's actually an attempt to take a very large body of code from a researcher on the CMTS project and translate it into Swift. And the particular code was basically exploring issues of energy landscape. And it was about 1,300 lines of shell code. So you look at the shell code, and half of the shell code basically tries to create input files to NAMD. So there's a lot of noise in doing that. And then the real logic of the flow of this 1,300 lines of code is kind of obscured in the midst of all the shell code. So with Swift, you can actually structure that in a very structured and hierarchical fashion. Now, true, you can sort of do this in the shell if you kind of code your work carefully. But by doing it in Swift, what you get out of this is these other benefits of location independence, of automated parallelism that the shell and typical other scripting languages don't give you. So if you look at this code, you sort of step back from it. At first glance, it looks kind of like C. It looks kind of like any other functional language. And we'll show you in just a moment how things like this are interpreted in parallel. But this in a nutshell in front of you is kind of the end goal of one of the thrusts of the Cyberinfrastructure effort on the CMTS project. It's basically to convert codes from ad hoc approaches into a more structured approach, and then create libraries of these kinds of tools that are reusable, shareable, trackable, and that themselves give you greater productivity when you use them alone, but also give you much greater collaborative potential when you use them as a group. Because now you can also not only tag the inputs and outputs of these scripts with metadata, but you can also tag the scripts themselves and use the tags to discover scripts in library repositories and things like that. Now, to sort of say where we are, we're not yet at the point where we've really achieved everything I'm talking about. So Swift as a language exists. We're now at the stage where we're really trying to get it into the culture of many different scientific groups across many disciplines. Okay, so CMTS is one of the engagements we have to try to really test this concept at the next level of scale. So today, we can't actually show you big libraries of existing scripts across many sciences or even within molecular dynamics, but this is where we're heading, and this is really the transition of our phase one center here to move on from the point of view of cyber infrastructure. And one of the things we really want to do, starting this summer, is to really engage with you and your teams to sort of take this concept back, see how well it applies in your organizations, and have a discussion with us about starting to first do some exploratory test cases, and then start seeing if we can actually construct libraries and see if we can find and define and make libraries that have broad reusability at different levels, within the community. Okay, so this is kind of the cyber infrastructure vision of the CMTS project. This is basically what we are in the middle of building. Some of this works, some of this has piece parts that work that haven't been fully interconnected yet, but this slide sort of says where we're going. And it's kind of a vignette that sort of starts with you, the researcher, developing your workflow into a structured script, like you saw that energy landscape script. Okay? So you write your script in a language like Swift. We're going to call this script just script. And the data set we're going to process here is energy landscape 1.trajectory. So you basically invoke the script as a function in Swift. Swift then basically is going to, take the name energy landscape.trajectory, and this by the way, this dotted part is one of the, or this step 2 is one of the pieces that we're still integrating here. So, but the idea here is then, instead of Swift just taking a file name, the idea is to now treat that file name as a logical data set without having to tie it to where that file lives. That file may be on your cluster, it may be somewhere out in the Exceed network, it may be on a campus server, it may be on the server of one of your collaborators that you have access to. So look it up in a file repository. So we use metadata to not only say what a file is, but where a file is. Then we also are in the process of trying to make heavy leverage of other cyber infrastructure components. So my team is actually a collaborator with a larger team called the Globus Project. So many of you may have heard about Globus or used Globus. But one of the most exciting things that Globus has developed in the past couple of years is the notion of taking its services and moving them into the cloud. So you can basically go to a website and use Globus's first cloud-based service, which is file transfer. So this is kind of a remarkable but simple piece of cyber infrastructure that takes all the complexities of moving big data sets from one machine to another and makes it as easy as clicking in a web interface and say, move this collection of data from here to here and tell me when you're done. So if you have to move several terabytes from one machine to another, you basically go to Globus Online, locate your data sets in a Finder-like interface. So very much like using Mac Finder or Windows Explorer, you navigate for your data set across many diverse servers. So you can basically say, well, connect to my resources here on my campus. I'll give you my campus login for that. Then connect to the Exceed system, and you can see all of the different Exceed or even Blue Waters servers, in Globus Online, and then navigate and move your files. And like Swift, Globus Online makes distribution transparent, it makes retry transparent, and it actually has kind of not only a network of servers behind it, but also has a network of people that if your data, if you say move a terabyte and that's going to take a day, and that request fails and it's not retryable, that error propagates to a support team that actually tries to really make transparent the job of getting your files from one place to another. So in this broader vision, we're actually trying to get Swift into that same kind of mode. So Globus Online defines what it calls endpoints. So the places where your data lives, to Globus Online is an endpoint. You get on the web interface and you say, find the endpoint on my campus, find the endpoint on my collaborator's campus, and those are called storage endpoints. We're trying to bring into it the concept of an execution endpoint. So much like you could find a data server, you could also find a cluster execution resource and connect you there. But this slide so far is showing just the use of that service as one of the many ways that Swift can move data. Okay, then the next step is actually run the application. We'll come back and talk about that a little bit more. Move the results back, so the place you ran may not be the place where you want your final results to reside. So your data will be moved back to a storage location. And then lastly, the collaboration-wide catalogs that store both metadata and provenance about your run will be updated. Okay, so this is where we're going. Okay, but the part I'm going to now spend more time talking to you about is really part 0, which is develop your script. Okay. So here's a kind of a canonical case of using Swift. So Swift kind of got its origins from what we call many-task computing. Not so much the computing model of running a small number of very large simulations, but running a very large number of more modest-sized simulations. So one of the early examples we did was in molecular docking. So if you have several proteins that are sort of implicated in some kind of disease or other syndrome, and you have a large number of ligands that you're looking at to see if they're good binding candidates for that ligand, the particular researchers we worked with here used a tool called Doc 6.0 or 6.2 to do that docking. So they would take a ligand library, I think it was from the open source Zinc library, and then they would build the doc descriptions of their molecules, and they would basically say, now I want to run 1 million instances of the doc program. Each doc would take anywhere from a few seconds to many minutes. So you're right off the bat, you have that sort of issue of dealing with disparate time lengths of your runs. And basically wanted to express this as kind of a simple Swift script and basically get these 1 million jobs issued from simple loops like we showed you before. And then we sort of went from there to try to apply that across a wide set of science domains. So we're doing work like this in climate science, in energy science, in power grid modeling, and in a couple of other areas that are closer to computational chemistry and molecular dynamics. Okay, so here's a script that we wrote quite a while back. In fact, Glenn Hockey was on this project, one of your colleagues over here, and basically did a lot of this work here in collaboration with Tobin Sosnick and Carl Fried, who were also collaborators on CMTS. So the problem here was one of doing large numbers of simulations. And the main thing I want you to take back from looking at this fragment of Swift code is how easy it should be for you to do a parameter sweep. So if a lot of your work is involving parameter sweeps, you want to make it very easy to express those in a structured manner. We can really see the logic of what you're trying to accomplish. And the other important take back here is to sort of note that unlike C, which uses a for statement, the sort of the workhorse parallel construct of Swift is called for each. So using for each, you can basically take a set of members of a data set, of a data collection, and iterate across them in parallel. And if you nest them, then the entire computation goes in parallel. So all the combinations of your parameter suite that you're expressing with these nested loops are essentially executed conceptually in parallel. So for example, this particular example, which is a bit contrived, generates 300,000 tasks. Now, if you don't have 300,000 compute cores, the Swift runtime system is going to throttle, and sort of schedule the execution of all of that work across the resources that you define for it. So now what I'd like to do is sort of dive a little bit, into Swift to try to give you sort of a feeling for what programming in this is like. And just as a preview, we're going to have a lab this afternoon, I think around 3 or 3:30, where we're going to actually give you a hands-on taste of this. With half of the lab will be very, very trivial, simple examples like this, so you can just sort of get a feel for the language itself, and then there'll be another module in there that actually does like a NAMD parameter sweep, so you can actually see how you would begin to translate some of the work that you do today into this kind of structured manner. Okay, so the first point I want to make in this very simple Swift example is another illustration of what I talked about before, which is kind of pervasive but implicit parallelism. So in any block of assignment statements that you're going to do in Swift, in other words, in any body of a function, all of the statements inside that block conceptually run in parallel. So that's what I mean by implicit parallelism. I didn't have to say that function f and g can run concurrently. And the way Swift determines that in its runtime system, and the way it does that is through a lower level programming model called data flow. So what we mean by data flow is that basically it's the availability of data that drives execution. So Swift uses a concept from computer science that really was developed in the late 70s in the MIT AI lab in the Lisp community. So Lisp is a very regular structured language. Everything is basically functions. So the sort of the data constructs in Lisp are very elemental and simple, but very regular and extensible. And what Lisp researchers were looking for a way to do was, even back in the 70s, they were looking to say, how can we start to leverage parallel computing? So they came up with this concept of the future, which is basically a variable that, in addition to having a value, it also has a state. And the state says, does the variable have a value yet or not? Okay, so in Swift, every variable has this property of being a future. Okay, so in other words, in Swift, every variable has a state. It's either set or not set. And like many functional programming languages, in Swift, variables are write once. Okay, so in other words, once you set the variable in a given function invocation, you can't change it. Okay, so that's a little bit of a mind bender when you start, programming with it for the first time. So here you can say j equals f of I, but I couldn't later say j equals g of I. Swift would say, that variable's already set. But the benefit you get from using this write once programming semantics is now the Swift runtime system can automatically know what's set and what's not, and hence it could know what can run in parallel and what has to wait for something else to be computed. Okay? So while I said that writing Swift looks a lot like C, once you really start writing it, it doesn't feel like C anymore. You really start to get the feel for how you express your overall flow of your computation just by writing functions, and kind of assuming that the runtime system will then sort out the order in which those functions can run. So for example, in here, it doesn't matter what statement you write first. Swift is going to run the evaluation of f and g, functions f and g here in parallel, and then it won't be able to compute r until variables j and k, which have the results of those functions, get a value. Okay, so this is kind of a simple tree of two functions and then a join. Okay, and just the last point is that is pervasive throughout the language, right? So no matter how long your Swift script is, when it starts running, conceptually, all the functions start getting evaluated. They all start firing. They all start evaluating their statements, and they're just going to randomly, or not, they're just going to, I should say, methodically block when data is not ready, waiting for data to be produced. So you could actually, if you actually looked at a trace of what your program is doing in Swift, and you have multiple nested levels of function call, the control is actually going down your call graph of your program and evaluating things until things block. Okay, so it's kind of fascinating when you really look at how the code flows. The code looks simple when you write it, which is the whole purpose of the language, but what's happening in the runtime system is actually very sophisticated in terms of parallel evaluation, throttling, synchronization, etc. Okay, so we already talked about computing being done in parallel. I also mentioned earlier that Swift is simple. It only has 4 basic data types. So it has booleans, ints, floats, and strings. Strings are very simple and dynamic. They're much more like Python strings than like C strings. So they're you don't have to sort of worry about the minutia of taking them apart and moving them and stuff like that. It has more or less a single kind of structuring construct, but it has a couple of ways to express that. So we have structs and arrays, just like you have in C. But they're very dynamic. So our Swift arrays are all really an associative hash table. So you access them looking like array, plain old array code, but they really function more like a Perl or a Python, hash or table. And every data cell, meaning every scalar variable and every element of an array or structure, is really a future. So that's what gives the language its pervasive parallelism, that no matter what your data is, it's going to basically block until the data is ready. It has only a few simple control structures, so the for each is very heavily used. There actually is a serial version of for each called iterate that we may in future kind of deprecate out of the language. And it has a simple if and switch context, so you can do simple amounts of control flow and conditional expressions in your code. And then it has a sort of a kind of a crude, simple, but growing library of basic functions. And again, the concept here is not so much that you're going to write all of your logic in Swift. We really want you to write your high-level logic in Swift. So if you have, today detailed shell, Perl, Python codes that construct your parameter files, the concept in Swift is by all means keep using those. Use those to kind of encapsulate the lower level details of your science logic, especially the details that are machine independent, the details that just concern the translation of your science logic into the tool set that you're using. Leave those as modules and then call those as Swift functions. So I'm going to actually go back to here one more. There's a couple other points I wanted to make. So one important point is that I really haven't covered yet is another very central aspect of programming in Swift is that its primary intent is as a workflow language for taking running external applications, NAMD, BLAST, LAMPS, GROMACS, dpoly, whatever you're using, and basically what it's going to let you do is to encapsulate those tools as if they were functions in the language. And part of that encapsulation means expressing the files, the data sets that go into and come out of those tools as if they are variables in the language. Okay, so Swift has a concept that is unique to it that you won't see in other languages of mapping external file data to in memory or in script names. Okay, so in Swift, when you have a file that could be named like namd.in or namd.conf in your environment, you might call that file just conf as a variable in C, but you want to map it to the specific file that you're going to use in your environment. And we'll see a lot more of this in the lab when we try this out. But so that's when I said there were a couple of primitive data types, and I mentioned before, Boolean through string. There's actually another type called file, which is a very commonly used one in Swift. So almost everything you do is going to deal with files going into and coming out of applications. So there's a data type called file that you declare to represent that, and then there's a process of mapping, which takes a set of scalar variables that are files or a set of array variables and things like that, and maps them to the names that those variables should represent in the outside world, meaning the world outside of your script. Okay, so the programming model, this is kind of an important part to really understand here, that the programming model concerns what you do as a Swift programmer is you basically say, here are the files I have to manipulate, here are the applications that I have to manipulate. I declare all that in Swift, and then I describe my logic as if it's in-memory code. So it looks kind of like in-memory scripting, but what it's really accomplishing is the coordination of the execution of external programs and the moving of data into and out of those external programs. So I'm going to briefly mention that the Swift we're going to use today is really the first generation Swift. Under some DOE funding in the Exascale program, we've taken the same programming model and now asked the question, can we take this, what we believe to be a productive data flow manner of implicitly parallel programming, and now start attacking in-memory problems. So I just said a moment ago that Swift largely moves files in and out of applications. Swift 2.0 is experimenting with how can we retain all that, but also support nicely just plain old in-memory programming, the invocation of library functions and the passing of the data structures that they require and that they produce between them, and to still have this notion of implicitly parallel programming. So we have a fully functional Swift 2.0 prototype running that's available for you to experiment with and download that actually implements this model. And what we were trying to achieve here, first of all, was scalability. So earlier I mentioned this programming concept called many-task computing. And in many-task computing, it's exactly what its name says. In some sense, it's it's kind of an extension of the concept that we started with in the 80s, 90s, called high-throughput computing, which was is basically running large numbers of application codes across a set of distributed resources. So many-task computing is exactly the same thing, but it simply implies that the granularity of the task we're running is going to shrink now. So we're going to try to let you not just run, hundreds of one-hour jobs, but we're going to let you run hundreds of thousands or millions of 10-second jobs. Okay, and what I've seen in computational chemistry and molecular dynamics is that the task duration of the apps you need to run really spans the gamut from multi-days to sub-second. And so Swift 2.0 is trying to address that. And in a nutshell, what we've gone from is a Swift 1.0 interpreter that can push out maybe 500 tasks per second to a 2.0 version that can go well over 1 million tasks per second. Okay, so the goal here is to address the larger and larger machines that are becoming available to the community. So for example, in Swift, if let's say you have a Cray system, we have a Cray here called Beagle that has about 18,000 cores. So if you're running many tasks computing on 18,000 cores, the particular example we were playing with at the time was in land use modeling. We have a application that runs in a few minutes, so each invocation takes a few minutes of runtime. If you're trying to keep 18,000 cores busy with, say, a 1-minute task, you need to be able to pump out 18,000 tasks per minute. So Swift 1.0 was really just at the edge. With 500 tasks per second, we could fill an 18,000 core Cray with, say, 4-minute tasks, but not with 1-minute tasks. Okay? So that was the goal of Swift 2.0. And in a nutshell, we achieved that by making the actual interpretation of Swift itself fully parallel. Okay, so in 2.0, in 1.0, Swift is run by a single Java virtual machine that can use all the cores on one node, but can't use many nodes to interpret your actual program. And in Swift 2.0 now, Swift itself is an MPI code that can run across as many nodes as you give it. So it runs as a big MPI program, and it divides up all the MPI worker ranks between actually running application code and running the Swift engine logic to do the program interpretation. So for example, we could go to Blue Waters, take over 100,000 cores, use 1,000 cores to actually interpret your Swift program, spitting out our 1 million tasks per second. And then we could use the other 99,000 cores for running your application code. Okay, so that's the main advance we're trying to do. Those are the two main advances we're achieving in 2.0. I'm not going to say any more about that. I'm actually going to try to wrap up here because I think we've pretty much expressed most of the concepts. The concept of encapsulation that this slide is showing is really the idea of taking your application code, your NAMD, and giving it a functional interface so that we can call it like a function as opposed to a command line. And we'll see in the lab how that looks. Actually, we'll see it right here. So this is kind of a simplified version of Glenn's protein simulation, the simulated annealing code. So we just kind of renamed it to PSIM to fit on the slide nicely. So let's say PSIM is your NAMD, it's your application program. So what you're going to do here is, this is the command line you want to really invoke. So this would be the kind of command line you have in your shell script today. In Swift, you're going to give it a functional header. So you're really going to invoke it by using this, give it a function name called predict. But when predict is invoked by Swift, Swift knows through this application program definition that it should invoke this command line. Okay, so I said earlier that one of the things you do in Swift is you map your external programs to Swift functions, and this is the syntax that you use to express it. So it's through this encapsulation. In other words, what we do is we take this kind of messy command line that has arbitrary kinds of passing conventions, plus the fact that many of your codes, most of your codes, get really the meat of their parameters from configuration files, and we give it a functional interface, and then we hide below that interface the issues of generating the command line and generating the config files. And so when you're trying to encapsulate your lower level tools so that you can then express them as kind of clean structured workflows, you have to sort of go through this thought process of what are the salient variables that I need to do or need to change or adjust or vary, say in a parameter suite, when you're invoking lots of copies of your science app, you do this kind of command line mapping. Okay? And then the net effect of execution is now doing many simulations, and then so what this slide also shows here is one of the most common patterns in Swift programming, of running lots of things, then summarizing the results, and then potentially taking this entire two-level workflow and gluing it into a larger workflow where you may be doing, a whole chain of these kinds of, basically map your work out, reduce it, map, and reduce. So, it's obviously, very similar to the map-reduce programming model that you may have heard of in, coming out of Google and being used through Hadoop in a lot of cloud computing and cluster computing. So this is exactly what Swift is doing. We don't call it MapReduce because it's basically just functional programming. It's, run a bunch of functions, reduce their output, do it again. Do it iteratively, do it sequentially, through many stages and things like that. Okay. I'm not going to say too much about this next concept, but I mentioned that you work in Swift by mapping your files to data. The way you would use Swift's struct capability is if you have a set of files in your environment that are all related together. Like let's say a NAMD run takes 3 different files to run. You need a PDB file, you might need a conf file, you need some kind of other molecule description file. You may want to bundle those up as one object, give them, call it a struct in Swift, and then we use a mapper to associate. This particular example comes from a different domain. It's functional MRI research that has kind of a similar need for taking what's on disk, in your disk directories and expressing it in much cleaner structure. So you go from this notion of a complex domain-specific structure on disk to a set of struct definitions in your Swift program to express the structure that's out there. And what's nice about this sometimes is that you can invoke a tool that needs 10 files and give it a single argument, which is a structure that represents those 10 files. And it kind of, again, simplifies the level of your programming. Okay, so I'm going to close with this brief overview. This is sort of the much more under development experimental part of our whole overall project. But this is what I meant in a nutshell by tagging. So we're basically experimenting with 2 simple little commands, tag and locate. In other words, put a tag on an object and then look up an object by a tag. Okay, so the goal is very simply to be able to associate arbitrary name-value pairs with your data sets and with your scripts and codes, your library objects basically, and then to look them up with simple logical expressions that are the key to your science. So the vision we're trying to get to is if you could imagine all of your computational runs being cataloged and then at the end tagged with some kind of metadata that describes what they did, maybe some science derivations about the salient results that the quantitative results that they achieved in a given run. You would express that all as name-value pairs and then be able to look that up in a big search. So in some sense, this would be like a structured Google for your entire knowledge base, for your domain, your world. Okay, and that's sort of where we're trying to get to now, to knit this concept of structured programming for, basically making structured what has traditionally been very irregular, messy, and unstructured to date, and then integrate that with metadata and provenance tracking to really give you that second level of productivity. The ability to collaborate by taking advantage of the new, regularity of the way you're expressing your science computations. Okay, so I'm going to close with that, and would be delighted to take questions either now or later, and look forward to working with you all. Any questions that you'd like to bring up right now?
So, do I understand correctly that one thing that this program is able to do is queue jobs that you have to nodes that you've been allocated?
Yes.
Okay.
Yeah. So
that
very
seems really useful.
Yeah. So so I guess I should have brought that out very explicitly. Is that Swift basically hides from you the issues of dealing with the queuing systems of your environment. So for example, if you're on, like say, Kraken on the Exceed network and you're using QSub to formulate your jobs, you might move to Stampede later and you'll have to use SBatch to submit your jobs.
Yeah.
You know, similar but different, right? So we want to abstract that. So Swift has drivers basically. The Swift runtime system has drivers for that encapsulate the interface to the scheduler and drivers that encapsulate the interface to data management. Okay, so you specify a PBS driver, a Slurm driver, whatever, and that's all basically isolated from your science logic code in a configuration file that's more typically developed by a system administrator and put into like a configuration library for the site you're using. Okay. And then Swift will generate the QSub or the SBatch or whatever's needed to submit your work on a given cluster, and that's all hidden and abstracted from you.
The other thing I was wondering is does it can it allocate nodes like dynamically?
Yes.
Okay.
Yeah,
so like if you no
these-
longer need some, it can like take them off, or if you need more,
Yes.
it can. Okay.
Yes, yes. So in these configuration files, you say what type of driver, what type of provider you're using to talk to a given cluster, and then you give it sort of parameters that say the units of allocation. You know, so I can say get all my nodes in one big allocation, one job, or I can say get my nodes on demand as my program issues functions. Then it will go and in turn do the Q subs needed. So if you start off with only 10 wide parallelism at the beginning of your program, you do some analysis and then you branch out to 1,000 wide. You know, in the runtime system, it'll sort of say, oh, now I need to go from my 10 jobs to 1,000 jobs, and it will put out the Q subs to get those resources for you.
And another thing is that oftentimes like the fewer nodes you ask for, the quicker you get on the queue. So if you basically just like give me as many as you can, give me, but I'll take more.
Yeah. So the question really is, I'll translate the question into: does Swift know how to game the scheduler? And the answer is
recorded.
The answer is yes, sort of. Okay, in the sense that in these parameter files, you can basically specify ranges of allocation. There's actually a mode that says when the program brings to the runtime system requests to run jobs, Swift can issue a spectrum of job sizes into the scheduler, ranging from smaller to larger, because a given scheduler may favor one type versus the other. So we want to get throughput for the user, so we'll say, just send a bunch of opportunistic requests to the scheduler and let the scheduler sort it out. But it's a topic of a bunch of research to try to figure that out.
Programs like NAMD and other simulation software, are they able to handle like if you suddenly change the number of processors a job is running on in the middle?
No.
Okay.
So Swift doesn't do anything to change the behavior of the application. The question was basically whether Swift can adapt to dynamic changes in the needs of a tool as it's running.
Okay.
I'm not sure if the people remotely can hear questions. If this is
Probably can't. That's right.
Okay, sorry if I haven't been
That's
repeating
okay.
everything. So Swift doesn't do anything to improve the behavior in any way of the programs that it's running. So what it can do to get these, what I talked about in terms of dynamic expansion and contraction of the running resource pool, it only does that in terms of running n copies of NAMD.
Yeah. So.
Okay. So if your workflow has 1,000
You can
NAMD,
say, okay, I have more nodes now. I can launch these things, but you can't say, oh, I'm going to expand the current simulation I'm running to suddenly run on 100.
No, because NAMD itself doesn't have the dynamic control, or very few tools, none that I'm aware of.
It's too bad, but it still sounds really useful.
We should probably get going.
Okay.
Mike. So I want to just emphasize, I'm actually
Should we wrap it?